Welcome back. We're on to section 5.3, still talking about relations. And now we're going to start proving properties of relations and the various operations on them. For your reference, I've already written on the board the main definitions that we've seen before. R is a relation from x to y, meaning that R is a subset of x cross y. The inverse relation, your AB is in the inverse of R if and only if BA is in R. The identity relation on X, A comma B is in that identity relation if and only if A equals B and A is in X. And composition, A comma B is in S circle R if and only if there is a C where A comma C is in R and C comma B is in S. And one other comment that we're going to use repeatedly, relations are sets. When we're specifically, they're sets of ordered pairs. Nothing, no other kind of object other than an ordered pair is in a relation. So if you're trying to prove that one relation is a subset of another or equal to another relation, instead of fixing an arbitrary object, as the proof templates have told you to do in the past, it suffices and is far preferable to fix an arbitrary ordered pair and then go through all the logic. And we'll see, I'll do some sample proofs here, just a few sample proofs, and then there'll be some kind of activity where you try a bunch of proofs yourself to get used to everything. Memorize definitions, of course, and all the old definitions, all the old proof templates are still in play as well. They all interact with each other. Let's do something. Let's prove something. And there's in the book and so on in the handout, there's going to be the closure theorem for relations, the theorem on relations that has all sorts of properties. I won't write those on the board because you have access to them, but I'll write the ones I'm proving. Prove for all relations R inverse is equal to R. So the inverse of the inverse gives the original relation back. Proof. It's a universal statement to be proved about all relations. So we have to fix, so let's say let R be a particular fixed relation. You could also say fix a relation R if you want a less verbose sentence. And we'll prove this guy. And the proofs might look strange until you remember everything is a set of ordered pairs. So if you want to show two relations are equal, you have to show that they're equal as sets. So we're going to do a set equality proof, and I'm going to use a chain proof. In this case, I think a chain proof is going to work very well. And here's where this comment comes in. Instead of fixing an arbitrary x and showing it's a member of one if and only if it's a member of the other, we know everything in these relations are ordered pairs. So let's fix an arbitrary ordered pair. X comma y. And what we're going to do for the chain proof is we're going to show that that ordered pair is in the left-hand set, the left-hand relation, R inverse, if and only if that same ordered pair is in the right-hand relation. And we're going to do it with a chain of known if and only ifs. We know, and you just have to peel the definitions off one at a time. So for the inverse, in this case it's not the inverse of R, it's the inverse of R inverse. But what does it mean? So x, y is a member of R inverse means, using a single definition, that y comma x is a member of this thing, it's a member of R inverse, by definition of inverse. This inverse, okay? And then I get to use the definition of this inverse, say, well, y comma x is in R inverse, by definition, if and only if x comma y is in R. And that's it. So that was a short one. You could have also done subsets in both directions. That would have worked, but would have been rather longer, two-part proof. Sometimes you have to do that, though. But here, with chain proof worked out really, really well. Okay. Let's prove another one. Let's prove for all relations X and all sets, all relations R and all sets Z, I'm going to claim that R circle the identity relation on Z is a subset of R. Subset of R. Okay. All right, so let's try that. Proof. We'll fix the arbitrary relation R. Fix an arbitrary set Z. Note carefully, I'm not assuming R is a relation from Z to some other set. It's just a relation. All right, set of ordered pairs. That'll be important later. And we're going to prove this. Subset statement. All these relations are sets of ordered pairs. And so when I get to the subset, do the subset template, proof template for subsets, but instead of fixing an arbitrary X, because it's a relation, this is a relation, composition is a relation by definition, everything is a relation, I'm going to fix an arbitrary ordered pair. Little x comma y. And we're going to assume, following the template for the subsets, that x, y is a member of this left-hand set, whatever it may be. And we're going to prove that x, y must then be a member of the right-hand set. Okay. Now, what can we do? So we have to expand this definition, making appropriate substitutions over here. This is true for every A, B, and also, I should say, for every R, S. Okay, but in this case, it's not R and S, it's these two things. So we assumed what? We assumed there exists, you can call it whatever you want, maybe as well call it C. There exists a C such that I can go from X to C via this guy, IZ. So remember, you read it kind of right to left. And then I can go from C to Y by means of relation R. Okay, always have to watch out that you don't flip these and get them in the wrong order. Okay. All right, but that's the order. And all right, so now what? Another definition has appeared right here, the definition of identity relation. So let's see what that means. X comma C is NIZ means that those two objects are equal. X is equal to C. And the first guy, X, is in the set Z. Okay. Well, but now, because X is equal to C and CY is in R, what does that tell us? I can just substitute this c is equal to x. So I get that x comma y is in R, which was the goal. And so this didn't even get used. It was true, but I didn't need it. So we're done. That's that one. Now what you might have expected me to say is that R of IZ is actually equal to R. Let's think about that. Is that always true? You might think that it is, but I'm actually going to say that it's not. And we can disprove something. How would we disprove it? Well, we'd have to show, sort of imagining this was an equal instead of a subset, negate the whole thing, because we think it's false. We'd have to show there exists a relation R, there exists a set Z, where basically, since this subset, we just finished proving this works. Let's see if we could get one where R was not a subset of the other one. Okay. So we need an example. And also, what does this mean? If you negate the definition of subset, keeping in mind this is a relation, that means we have to find an example of an xy ordered pair where x comma y is in R, but it's not in the composition. Okay. Well, we can do that by using an example. We have to give an example. There's all these existence statements. So give an example. Choose an example. And lots of things, but let's just choose a sort of something kind of easy. So I'll just make an R. Maybe R is like 1, 2, 2, 3. Little tiny relation there. And the crucial thing you have to come up with is that this, maybe if the set Z was too small, you get to choose Z as well. Let's think about what would happen if we picked, what if Z was 1, 2, the set 1, 2? Well, now you can just directly calculate, like we did before, R circle IZ. First of all, what's IZ? IZ is 1, 1, 2, 2, and nothing else. And therefore, if I'm calculating this composition, which in a finite set, you don't have to prove it, you just do the calculation and write the answer, I can go from 1 to 1, and then I went from 1 to 2, so I get that. And here I can go from 2 to 2 and then 2 to 3. Uh-oh. So actually, that did work. The one that didn't work. All right, but this is good because it's not like your first example always works. You might have to try different things. All right, so that didn't quite work out because it was equal when I was trying to get it to be not equal. So that's fine. Let's choose another Z. Maybe I was too ambitious there. Why don't we just choose Z to be 3? Singleton 3. So then the identity on this guy is just 3, 3. And then I can calculate this composition. And what's going to happen here? Remember, IZ happens first. So I go from 3 to 3. And now I look in R, but there is no first component that's a 3. So this is the empty set, which is not equal to R. Okay. So we did it. And so just if you want to see this, like notice that to have a fully detailed proof of this, for instance, 1, 2 is in R, but 1, 2 is not in the empty set. If you want to expand this guy out, and so you've done it. And this shows, we have these examples for disproofs or whatever. You don't always hit it the first time. Like sometimes you accidentally get something where it doesn't give you the property you want, and you just try something else. Okay, that happens all the time. Now you might be disturbed that it didn't work. There is a variation of this in the theorem where it does work, which I'll just state, and this will be an exercise or something. If R is a relation from X to Y, if you have that extra information, then it actually is the case. You have to do it in the right order. But if you do R circle I sub X, that's equal to R. Equal. And if you do I Y circle R, that's equal to R. So check that. That'll be like someone will do that as an exercise or something. This shows you that in general, it get one subset direction, but not this direction in general. Okay. Speaking of that, let's do at least one. This will be the last sample proof for this segment. Let's do one proof that uses that definition. And I guess I can get rid of all this. Let's start writing it over here. All right, so example, or sample proof. Prove for all R, for all S, for all X, for all Y, for all Z, if R is a relation from X to Y, and S is a relation from Y to Z, then S circle R is a relation from X to Z. And there's a little cartoon picture that's supposed to make this highly believable. If you had arrow diagrams where R is happening first, mapping inputs from X to outputs from Y, and S is happening second, mapping Y to Z, and then S circle R, remember, is this composition that goes like that. Okay, that's what this is saying. But again, an arrow diagram is just an example. That doesn't serve as a proof that it's always going to work. One thing we don't have to worry about, the way I define things, by definition, this is a relation. So you have to check that. The thing that's being asserted that has to be checked when we get there is it's from X to Z. Okay. All right, so we cranked through this. We've got all these quantifiers. We're going to fix arbitrary R, S, X, Y, Z. And if then. Next thing that's happening in the statement is if then. So do a direct proof. We're going to say assume all this stuff. Prove that. So assume R is a relation from X to Y, and S is a relation from Y to Z. Prove S circle R is a relation from X to Z. Let's see if that's, yeah, that should be visible. All right, and so now we get to expand this definition a bunch of times. So we assumed R is a subset of X cross Y. And S is a subset of Y cross Z. And we have to prove that S circle R is a subset of X cross Z. All right, let me let's pause this for just a second. Okay, so there we go. There's our proof structure. The new goal is a subset statement. So we launch into the subset proof template. But what? Wait. So everything's in a relation. This is a relation anyway. So it's this actually. So we're going to do it with ordered pairs. Fix arbitrary ordered pair. Let's just call it AB. Any letter you like. Assume that that ordered pair is in the left-hand relation, S circle R. And we're going to have to prove that that same ordered pair is in the right-hand set, X cross Z. Okay. And you just keep going. That's always what you do. And it's like, well, looking at the last few things you've written, are there more definitions to expand? And yes, there are. This is a definition, this is a definition. So what do they mean? We assumed, all right, this is a word-for-word copy of this one. So we assumed there is a C, there exists a C, where AC is in R, and CB is in S. Okay, R first, S second, so to speak. And what does this mean? And here you have to think back to the set theory chapter. We covered this at the very end when we did product sets, but it was a while ago. This means that A is in X and B is in Z. So that's the goal. Goal is an and statement. Okay. And so we have to do two parts. We're going to blindly follow these templates. So part one, prove A is an X. How are we going to do that? So, well, we have to keep track of all this stuff we've assumed. Got this and this. And from before, we have this and we have this. Okay. Well, let's take a look. A appears here. So let's start here. A, C, and R. But we have already known that R is a subset of that. So that's a known subset statement. So we can do this deduction, then therefore AC is in X cross Y. What does that mean? That's the same definition almost that we just had here. That means that A is in X and C is in Y. So in particular, it's a known and statement. The first part is true. A is in X. That was the goal of part one. All right, and part two is almost the same. We still have to do it to have a complete proof. We have to prove that B is in Z. And now we're going to just, hopefully, we'll just use this. So since CB is in S, here, we assume that, and S is a subset of Y cross Z, we deduce that CB is in Y cross Z, and And that means that C is in Y and B is in Z. So what we need, the second half of that and, is the goal that B is in Z. All right, so that's that. All right, so there's way more properties, and there'll be exercises and activities where you prove them. The one, you can look at them, I've mentioned one that's especially important that I won't prove here, but I'll just draw your attention to because it's super crucial. We already pointed out earlier that usually, in most situations, S circle R is not the same relation as R circle S. Composition of relations is not commutative. But for all relations, let's make sure I'm not remembering that wrong. Yeah, even without worrying about the X's and the Y's and the Z's, for all relations, RST, you do have something else called associativity of composition that does work. That's a very interesting proof, as a matter of fact. So this is saying relation composition isn't commutative, but this one is saying, although I haven't proved it, that relation composition is associative. You can move the parentheses without changing the order. And as a special case of that, when we do functions, so function composition will be associative as well. And you've got I think I already mentioned the identity property. If R is a relation from X to Y, composing with the identity in the right way does give you R back. Okay, that's the end of that one. See you later.